Section 6.8, the complex numbers. So the objective today is going to be to add, subtract, multiply, and divide complex numbers. Now first, we have to actually come up with a definition of what this is. Well, the set of complex numbers includes the subsets of real and imaginary numbers. So for example, we remember like the number 3. Well, that's a real number. The number 2i, that's an imaginary number. But what if I had some expression like 3 plus 2i? You know how we used to have like 3 plus x. Well, 3 plus 2i, there's a real component and there's an imaginary component. So here we could say that a is 3, call that a, and we'll call this 2 here, we'll call that b. And we could say that a is the real part and b is called the imaginary part. And we write this as follows, in standard form, okay, in standard form. Whenever we have an answer, if there's a real and imaginary part, it's always written this way. So if the answer had a, say a negative, it could be like negative 2 plus 4i, or it could be 7 minus 3i. But either way, we still have a real, right? A real, and we also have an imaginary component each time. Okay, so a would be negative 2 here, a would be 7, b would be 4 here, b would be negative 3 here. Okay, so these are the b values, these are the a values. It's really important to be able to identify what a and b are because of their applications in engineering. And let's take a look at a simple example here where we're going to simplify addition and subtraction. So in the first one, we're going to have 2 plus 4i plus 3 minus 5i. And since this is addition, we're just going to add like terms. So the 2 plus the 3 gives me a 5 for part A, and then the 4i and a negative 5i is negative 1i, or just negative I. So in part A, it's 5 minus I. Part B, we have 6, but then we have a minus here. So what I'm going to do is make that a plus, and I'm going to make both of these opposite signs. So make that a negative, and make that a positive. So I'm really distributing the negative to both. And then I'll just add like terms. So 6 plus a negative 2 is going to give me a 4. And then negative 7i plus positive 4i is going to give me a negative 3i for part B. Again, for part B, this part I'm doing negative 7i and a positive 4i, giving me the negative 3i right here. Let's take a look at simplifying when we have multiplication. And what we want to remember is that these are binomials. And whenever you're multiplying binomials, you have to think about the fact that you're double distributing, or you're foiling in these cases. So start by foiling the first one out. First gives me 12, outer gives me negative 9i, inner gives me positive 8i, and last gives me negative 6i squared. Start by simplifying here. We're going to get minus I in the middle, right? These two terms add up to negative 1i. And then remember that this I squared, this component is really a negative 1. So this is really negative 6 times negative 1, which is just going to be positive 6. So in the end here, we can add this 12 and this 6 together to give us 18, and this simplifies to 18 minus I as our final answer for part A. For part B, we just have to remember that we need to FOIL this. We cannot distribute the square to each term. Part B is really saying the following. It's saying quantity 3 minus 5i times quantity 3 minus 5i. Now, if I were to multiply these two, I have to FOIL them. First, it's going to give me 9. Outer is negative 15i. Inner is negative 15i. And then last is going to be positive 25i squared. Combining the middle terms here, we're going to have 9 minus 30i. This being a negative 1 right here, I squared makes this minus 25. And then the 9 minus 25 is negative 16. And then minus 30i. Again, written in standard complex form. Finally, for part C, notice we're seeing 5 minus 2i, that quantity, times 5 plus 2i. And right away, we should recognize that this is an example of an answer you would get if you factored something that was difference of two squares, right? These are conjugates. Now, in the past, we had examples where it was like 5 plus radical 2 times 5 minus radical 2. And those were called binomial conjugates. What we call these are complex conjugates. Okay, so anything that's written in the form a plus or minus bi, like we see here, right? There's the plus and there's the minus. Those are called complex conjugates. And let's take a look at the answer and see what we notice here. What we're going to notice is that our answer simplifies very easily. When we FOIL, the first term gives us 25. But then the outer and inner are going to be 10i and negative 10i. So those are going to cancel. So I can write them, but they're going to end up canceling anyhow. And then the last term is going to give me negative 4i squared. So remembering that I squared is negative 1. This is negative 4 times negative 1, which is positive 4. So 25 plus 4, or simply 29. So for this problem, what we'll notice is that when we multiply two complex conjugates, the result is an integer value. So let's keep this in the back of our mind if we have to work with our denominators in a minute to get an integer in our denominator. So let's apply that rule that we were just thinking about. When dividing by a complex expression, multiply both numerator and denominator by the complex conjugate. This is analogous to the following. What if I had 2 over 3 plus root 5? Well, you would multiply by 3 minus root 5 over 3 minus root 5, right? The binomial conjugate. Well, the same thing occurs. If I have this with a complex denominator, like 2 over 3 plus 5i, well, we have to multiply by 3 minus 5i over 3 minus 5i. Okay, again, remembering to distribute this 2 to both terms, and in the denominator, we can FOIL that out. But the middle terms are going to cancel again, if you notice. Example 3 for here we'll take a look at. We should multiply this by 5 minus 3i over 5 minus 3i. So I'm going to start by rewriting it so I can see it a little bit better. And I'm going to multiply by 5 minus 3i over 5 minus 3i. Now, remember, put everything in parentheses so you remember that you need to FOIL the numerator. So the numerator, let's go ahead and FOIL this. This is going to become 20. Outer is going to give me minus 12i. Inner is going to give me minus 5i. And then last is going to be a negative negative, right? This negative times this negative is a positive. So it's going to be a positive 3i squared. All over. Now we FOIL, but we don't have to worry about the inner and outer. Because the outer is negative 15i, the inner is positive 15i. So when I do the outer and the inner, they cancel. So let's just multiply the last part next. So this is going to be negative 9i squared. Simplifying the numerator becomes 20 minus 17i, and this, remember, is a negative 1, so this is going to be a minus 3. The denominator, this being a negative 1, really makes this a plus 9, so this is going to be 25 plus 9. And what we'll notice for our answer, the 20 minus the 3 gives us 17, and then we have to carry down the minus 17i from right here, and this is all over 34. And what you'll notice is that both of the terms in the numerator can be divided by 17, and so can the denominator. So I could really just cancel or reduce by a factor of 17. Remember, what you're really doing is this. You're factoring out a 17. So a 1 remains in both of these spots. This is 1 minus 1i, or just 1 minus I. And 34 is really 17 times 2. So that's why these GCFs, remember, can cancel, because it's in all of the terms that can be taken out. So your final result ends up being 1 minus I over 2. Now, if I want to write that in standard form, I want to write it as A plus BI. Well, this becomes, ready? 1/2 minus 1/2 I. And that's a little bit difficult to see. Well, there's really a 1 right here in front of there. And I can say this 1 divided by 2, well, that's this 1/2 here. And then this 1 divided by this 2 is this 1/2 here. The negative sign carries down from the middle, and the I part carries down as well. So this would be my answer in standard complex form. So this tells me that A is 1/2, B is negative 1/2. This is the real component, this is the imaginary component of the complex number. Example 4 says determine the reciprocal of 7 minus 2i. Well, that's just 1 over 7 minus 2i. Well, this is telling you to use your logic. How do you simplify this? Multiply by the complex conjugate. So we have 7 plus 2i up top, because that doesn't change with the 1 there. The denominator becomes 49. Inner and outer cancel. It's going to be minus 4i squared. Well, this means plus 4, right? Because this is really a negative 1. So negative 4 and negative 1 is positive 4. So this denominator becomes 49 plus 4, which is just 53. So your answer is 7 plus 2i over 53. And now written in standard complex form, we have to break up the fraction. That's 7/53 plus 2/53 I. And that I is like its own variable in a sense. The 2/53 is like its coefficient. Okay, so the 2/53 is multiplying by the I. So I is really over 1. Keep that in mind. Example 5 says, for the function g of x equals x over quantity x plus 1 squared, determine g of 1 plus 3i. So remember, this means that I want to take whatever x was and replace it with this quantity. So that quantity needs to go there, and it needs to go in for that x right there, before we add 1 and square and do all that. So let's go ahead and see. So g of 1 plus 3i equals 1 plus 3i over, parentheses, 1 plus 3i plus 1, that whole thing's squared. Well, let's take a look now. The denominator becomes 2 plus 3i, right? So this is just 1 plus 3i over 2 plus 3i, that whole quantity squared. Well, I can't do much with this until I expand it. I need to make that denominator a little simpler. So I have to remember that 2 plus 3i squared is really 2 plus 3i, 2 plus 3i. Okay, so this denominator, again, is really written like this. 2 plus 3i, 2 plus 3i. Let's multiply that out. The numerator is still 1 plus 3i. The denominator becomes 4. Outer is going to give me 6i. Inner is going to give me 6i, giving me 12i. And then last is going to be plus 9i squared. Well, remembering that I squared is negative 1, it makes this really just minus 9. 4 minus 9 is going to give me negative 5. So in the denominator, I have negative 5 plus 12i. In the numerator, I still have the 1 plus 3i. So this is the result of simplifying this original expression as far as we can go to here and then down here. But now I have to remember that this is not written in standard complex form. I need to multiply this by the complex conjugate. So what is the complex conjugate of negative 5 plus 12i? It's negative 5 minus 12i over negative 5 minus 12i. Remembering in the numerator to FOIL, and in the denominator we FOIL, but the denominator we know that the middle terms are going to cancel, leaving us behind an integer value in the denominator. So the numerator FOILing gives me negative 5. Outer is negative 12i. Inner is going to give me negative 15i. And then last is going to be negative 36i squared. All over, negative 5 times negative 5 is 25. Outer and inner cancel. It's going to be 60i and negative 60i. Last term is minus 144i squared. At this point in time, it's just a matter of simplification. So let's go ahead and simplify. The numerator, a negative 36 times I squared, which is negative 1, is really positive 36. I'm going to do it like that. This becomes negative 27i. And a positive 36 and a negative 5 is going to give me positive 31. So the numerator simplifies into 31 minus 27i. The denominator, though, this is a negative 144 times this, which is really negative 1. That's a positive 144. So we have 25 plus 144, which is 169. In standard A plus BI form, my final answer becomes 31 over 169 minus 27 over 169i. And I can't reduce either of those fractions, so I leave this alone. And I can clearly see that I have a real part and I have an imaginary part here.